you ever wondered how a machine learning model gets better over time? Just like humans learn from experience, machine learning models also evolve and improve as they encounter new data and situations. In today's rapidly changing world, data is constantly shifting. What works today might not work tomorrow as customer behaviors change, market trends shift, and new patterns emerge. So do we need to build models from scratch every single time? The answer is no. In this video, we'll explore the powerful model evolution techniques that help your models become smarter, faster, and more accurate over time. Whether you're new to machine learning or an experienced practitioner, you'll gain a comprehensive understanding of how models evolve. Let's get started. Before we dive into the specific techniques, let's talk about why model evolution is so important in real-world applications. First, there's concept drift. Data distributions change over time. Think about how shopping patterns shifted after COVID-19. If your recommendation model is trained on old data, it might fail to capture new behaviors. Second, computational cost is a big concern. Training large models from scratch every time is expensive and time-consuming. Finally, data availability can be limited. Sometimes you only have access to small amounts of new data, making full retraining impractical. These challenges make model evolution techniques not just useful but essential for keeping your models relevant and efficient. Concept drift refers to the phenomenon where the statistical properties of the target variable change over time in unforeseen ways. For example, a model trained to predict movie preferences before a major cultural event might not perform well afterward as people's tastes shift. This makes it crucial for models to adapt to new data patterns. Ignoring concept drift can lead to poor predictions and lost opportunities. That's why model evolution techniques are designed to help models stay up to date and maintain high accuracy, even as the world around them changes. Training a machine learning model from scratch can be incredibly resource-intensive. It often requires powerful hardware, lots of memory, and significant time investment. For large datasets or complex models, this cost can quickly become prohibitive, especially if you need to update your model frequently. Model evolution techniques help address this by allowing you to reuse existing models and only update what's necessary, saving both time and computational resources. This efficiency is a key reason why these techniques are so valuable in practice. Many real-world scenarios, you might only have access to a small amount of new data at any given time. Retraining a model from scratch with limited data can lead to overfitting or poor generalization. Model evolution techniques are designed to make the most of the data you have, allowing your model to learn incrementally and adapt without needing the entire dataset. This makes them especially useful in environments where data arrives in small batches or is expensive to collect. Transfer learning is a powerful technique where a model developed for one task is reused as the starting point for a model on a second task. Instead of training a model from scratch, you leverage the knowledge the model has already gained. This is especially useful when you have limited data for the new task. For example, a model trained to recognize animals in images can be adapted to recognize specific breeds with much less data. Transfer learning saves time, reduces computational cost, and often leads to better performance. Fine-tuning is closely related to transfer learning. After transferring a pre-trained model to a new task, you can further train it on your specific dataset. This process adjusts the model's parameters to better fit the new data, improving accuracy and relevance. Fine-tuning is especially effective when the new task is similar to the original one. It allows you to get the best of both worlds, the general knowledge from the original model and the specific insights from your new data. Incremental learning, also known as lifelong learning, is a technique where a model learns continuously as new data becomes available. Instead of retraining from scratch, the model updates its knowledge incrementally. This is particularly useful in dynamic environments where data arrives in streams or batches. Incremental learning helps models stay current and adapt to new trends without forgetting what they've already learned, making it a key strategy for real-world machine learning application. Online learning is a specific form of incremental learning, where the model updates itself one data point at a time. This is ideal for scenarios where data arrives continuously, such as stock market predictions or real-time recommendation systems. Online learning allows the model to quickly adapt to new information, making it highly responsive to changing environments. It's a practical solution for applications that require immediate updates and real-time decision-making. Neural architecture search, or NAS, is an advanced technique where algorithms automatically design the best neural network architecture for a given task. Instead of manually selecting layers and connections, NAS explores different configurations to find the most effective structure. This approach can lead to highly optimized models that outperform hand-designed architectures. NAS is computationally intensive, but can yield significant improvements in accuracy and efficiency. Evolutionary algorithms are inspired by the process of natural selection. In this approach, multiple models are generated and evaluated, with the best performing ones selected to create the next generation. Over time, the population of models evolves to become more effective. This technique is particularly useful for optimizing complex models and discovering novel solutions that might not be found through traditional methods. Evolutionary algorithms bring a creative, adaptive edge to model evolution. Knowledge distillation is a technique where a large, complex model, the teacher, transfers its knowledge to a smaller, simpler model, the student. The student model learns to mimic the teacher's predictions, achieving similar performance with fewer resources. This approach is especially useful for deploying models on devices with limited computational power, such as smartphones or IoT devices. Knowledge distillation helps make advanced machine learning accessible and efficient. Ensemble methods combine multiple models to improve overall performance. By aggregating the predictions of several models, ensembles can reduce errors and increase robustness. Techniques like bagging, boosting, and stacking are popular ensemble strategies. These methods are particularly effective when individual models have different strengths and weaknesses, as the ensemble can balance them out for better results. Hyperparameter tuning is the process of finding the best settings for a model's parameters, such as learning rate or batch size. Automated techniques like grid search, random search, and Bayesian optimization can systematically explore different combinations to maximize performance. Proper hyperparameter tuning can make a significant difference in a model's accuracy and efficiency, ensuring that you get the most out of your chosen architecture. Active learning is a strategy where the model actively selects the most informative data points to learn from. Instead of passively receiving data, the model queries for labels on examples it finds most uncertain. This approach is especially useful when labeling data is expensive or time-consuming. Active learning helps models achieve high performance with less labeled data, making the learning process more efficient and targeted. Continual learning, also known as lifelong learning, enables models to learn from a continuous stream of data without forgetting previous knowledge. This is crucial for applications where the environment changes over time, such as robotics or personalized recommendations. Continual learning techniques help models adapt to new tasks while retaining what they've learned before, preventing the problem of catastrophic forgetting. Catastrophic forgetting occurs when a model loses previously learned information while learning new tasks. This is a common challenge in continual learning. Techniques such as rehearsal, regularization, and architectural changes are used to mitigate this problem. By addressing catastrophic forgetting, models can maintain their performance across multiple tasks and adapt to new information without losing valuable knowledge. Meta-learning, or learning to learn, is a technique where models are trained to quickly adapt to new tasks with minimal data. By learning the underlying structure of tasks, meta-learning enables rapid generalization. This approach is particularly valuable in scenarios where new tasks emerge frequently and data is scarce. Meta-learning pushes the boundaries of model evolution by making adaptation faster and more flexible. Self-supervised learning is a method where models generate their own labels from the data, allowing them to learn useful representations without manual annotation. This technique has gained popularity in natural language processing and computer vision, where labeled data can be scarce. Self-supervised learning enables models to leverage vast amounts of unlabeled data, accelerating the evolution process and improving performance. Semi-supervised learning combines a small amount of labeled data with a large amount of unlabeled data during training. This approach helps models learn more effectively when labeled data is limited or expensive to obtain. By leveraging both types of data, semi-supervised learning bridges the gap between supervised and unsupervised methods, making model evolution more practical in real-world scenarios. Domain adaptation is a technique that allows models trained on one domain to perform well on a different but related domain. For example, a model trained on photos from one country can be adapted to work with photos from another country. Domain adaptation techniques help models generalize better and reduce the need for extensive retraining, making them more versatile and robust. Regularization techniques are used to prevent overfitting and improve model generalization. Methods like dropout, weight decay, and early stopping help models avoid memorizing the training data and instead learn patterns that generalize to new data. Regularization is a fundamental part of model evolution, ensuring that models remain robust as they adapt to new information. Auto-pruning is the process of removing unnecessary parameters or connections from a neural network. This reduces the model's size and computational requirements without significantly affecting performance. Pruning is especially useful for deploying models on resource-constrained devices. By streamlining the model, pruning helps maintain efficiency as models evolve and grow more complex. Quantization is a technique that reduces the precision of the numbers used to represent model parameters. This can significantly decrease the memory and computational requirements of a model, making it suitable for deployment on edge devices. Quantization is an important step in model evolution, enabling advanced models to run efficiently in real-world environments. Automated machine learning, or AutoML, refers to the process of automating the end-to-end process of applying machine learning to real-world problems. AutoML systems can automatically select the best model, tune hyperparameters, and even pre-process data. This makes machine learning more accessible and accelerates the model evolution process, allowing practitioners to focus on higher-level tasks. Model monitoring involves tracking a model's performance over time to detect issues like concept drift, data quality problems, or declining accuracy. Continuous monitoring is essential for maintaining model effectiveness as data and environments change. By setting up alerts and regular evaluations, you can ensure that your models remain reliable and up-to-date. Training strategies determine when and how to update your models. Options include scheduled retraining, triggered retraining based on performance drops, or continuous retraining with new data. Choosing the right strategy depends on your application's needs and the rate of data change. Effective retraining ensures that your models stay accurate and relevant as new information becomes available. Deploying evolved models requires careful consideration of factors like latency, scalability, and resource constraints. Techniques such as model compression, pruning, and quantization help ensure that models run efficiently in production environments. Monitoring and updating deployed models is also crucial for maintaining performance over time. Model evolution techniques are used in a wide range of real-world applications, from personalized recommendations and fraud detection to autonomous vehicles and healthcare diagnostics. These techniques help models stay current, accurate, and efficient, enabling businesses and organizations to deliver better services and make smarter decisions. Wrap-up model evolution techniques are essential for keeping machine learning models relevant, accurate, and efficient in a rapidly changing world. From transfer learning and fine-tuning to advanced methods like neural architecture search and knowledge distillation, these strategies empower models to adapt and thrive. By understanding and applying these techniques, you can ensure that your models continue to deliver value, no matter how the data landscape evolves. Thanks for watching and keep exploring the exciting world of machine learning.